So, ladies and gentlemen, thank you very much and welcome to our little party here, or show, whatever we're going to call it. I'm Andreas Anetiadis. I bear the lofty title of CTO for the Mass Infrastructure Group, Sales, Mobility, put enough words in there. Basically, I have the opportunity to work on interesting things around the world, and this is something that's captured our interest for a very, very long time.
Bart van der Velde, I'm in the networking CTO office, essentially in engineering.
And we also need the clicker, of course. So just as a little bit of a story, because it bears, this work was started about 3 years ago?
Yes.
Exactly 3 years ago, in fact, February of 2020, by our late and very, very much missed colleague, Mark Gallagher, who first kind of started looking at the existence of QUIC in service provider networks and started examining how it behaves and whatever. Mark passed away about a year and a half ago, as you can tell, but his legacy and his work lives on, and we try to drive it as far forward as we like. And with that, a bit of an agenda. We're going to look at a bunch of different things today, starting with what we're calling the new internet. The new internet being how actual traffic is evolving on the internet today. We've been measuring the protocols in various parts of the world and at various times, and have been gaining some fairly interesting insights about how internet traffic is evolving and how that's challenging our assumptions as users. We're then going to try and go through a brief analysis of the protocol stacks that are emerging within this new internet and how they impact traffic behavior and what it does. Then Bart's going to take it and to talk to us about how that actually changes the way service providers have been dealing with their networks, or should change. And then finally, for the grand finale, we're going to talk to you about a toolkit that we've been working on and building, which allows us to actually deal with a lot of this, in certain ways, with a lot of this obfuscation that is happening in this world. And hopefully, it's going to be an interactive session. If you want to ask a question, hold it till the end. If you burning question, just ask it. And hopefully, we're not going to divert too much. So, with that, Mr. van der Velde. Oh no, I have to do the history slide. Yes, I forgot, because I added this yesterday. So I'm going to be showing my age here, but when Mr. Berners-Lee kind of started putting together the World Wide Web and HTTP 1.0, I did go to university with him, so it shows my age to a certain extent. There was not much that they could do about it. If you think about it, HTTP 1.1 and whatever, and Bruce Davey has written a really cool paper in his website that I would urge you all to read about it. It's really designed to work over a remote procedure call type of protocol, but there was no RPC protocol in the internet at the time. So what they do, they use TCP because that was the best reliable. But if you think about it, we were doing sessions upon sessions upon sessions, and it wasn't the most efficient way in the universe. Oh, and by the way, we were doing one session per element, and then we started getting multi-element pages and applications and whatnot. Not the most efficient way in the universe. So the need for speed drove the evolution first with Google going towards speedy, an evolution of TCP that most of you probably know. Didn't go very far, but it was a good starter to finally coming into QUIC. QUIC being a major transition because it's essentially, and we're going to talk about it in a lot more detail, an RPC protocol over UDP, where we move a lot of the flow control and everything into the application, into user space. It's a massive transition of where we started from with TCP to where we are today with QUIC. And it's important to keep this in mind as we go through this information.
Yes. So what we first want to do is walk you through a whole set of measurements we've done over the, let's say, last 3 years, looking at various service provider networks, primarily consumer-focused networks. And the first measurement we did was in 2020 with Mark, where essentially we got hold of a very large data set from a large carrier in the US. And lots of data behind this, lots more detail, but I'll spare you that and give you the highlights. Essentially, for all intents and purposes, all traffic is encrypted, right? There is no clear text traffic running on the internet, over 90%. The other big thing, which is not that surprisingly, but I think it's pretty impressive if you spell it out, over 70% we found was volume going to and from the cloud, with essentially 10 big logos dominating the space. And you essentially have this internet which has massive elephant destinations rather than elephant flows. Also, the utilization of DNS as effectively the control plane for anything that's running over the internet is quite impressive, right? If you look at the total amount of flows in this data set, 50% was essentially DNS queries flying back and forth. And we also, picked up, as we already said, on this rise of QUIC, where, winding back 3 years or 2.5 years, we saw roughly around 20% of the traffic being driven over QUIC. And we started to essentially realize that this is something that had legs, and we expected it to grow. I'm kind of giving you the last slide of the data set almost. But essentially, for us, this really means that the internet is converging on a new normal, where things are essentially carved up between the big logos you see here driving most of the volume, and then a very large chunk getting delivered over CDNs with a very small set of long tail traffic, right? So if you think about designing networks, this is really what you have to put in your base assumption if you want to look for efficiencies, et cetera, et cetera. So we also concluded that all of these big logos have plans or are implementing HTTP 3 and QUIC, so we were expecting very wide scale adoption there. And fast forwarding this a little bit to the start of 22, we did some measurements in Europe, a tier 1 mobile carrier, and we found that traffic essentially on QUIC had doubled. So 43% of volume driven over QUIC versus TCP. So a TCP/IP design assumption is valid to some extent, but not quite, because you're looking at roughly 50% of traffic. And you see that Facebook, YouTube have fully, essentially, for all intents and purposes, switched to delivery of their content over QUIC, which is a massive testimony to the fact that this protocol is delivering the needs that they are looking for in terms of user experience and overall quality of the content delivered over whatever network they have to run over.
And by the way, Google, you would expect, I mean, they invented QUIC, so they're kind of driving it that way. What was really impressive was Meta. They literally flipped from 0 to 90% overnight, over the span of like a month and a half, just by flipping, because it's mostly app-driven, by flipping their application to a QUIC stack, boom, gone.
And they can do that because the traffic driven over mobile is purely delivered over siloed apps on your phone, right? So if they change that stack, everybody's going to follow, which is a bit different from other endpoints like computers and what have you. So zooming in a little bit on this data, you can see that essentially the Meta world is QUICified, I'll say. YouTube, similar story. The big holdout really is today Netflix, right? They sit on a highly optimized TCP/IP stack. They've essentially built that out massively, but we obviously they're the ones to decide. We do expect them to make a move in this space at some point.
We know, because they use primarily the Google ABR player, that the QUIC stack is already included in their software. It's a question of just flipping a switch for them.
Yeah.
When and if they want it.
Exactly. So a bit more further zooming from a similar snapshot. So the big five are driving like 50% of traffic, and you really got an 80-20 rule established, right? With 40% of traffic being QUIC, volume on the left-hand side. Now on the right-hand side, we also looked at the flows you see cruising along on the network, and you actually see a broader inverse effect, which is, TCP IP sessions are the more chattier ones, the more, higher amount of sessions, when QUIC is actually less of the pie chart. And the reason primarily is that today the QUIC delivery is used for long sustained flows, video, content, etc. So there's no need to actually exercise some of the multi-session capabilities that QUIC also has. So a lot of IoT we suspect in those TCP transactions, but we actually expect that that QUIC vector of being able to do a lot of parallel sessions will start kicking in as some of those elements start migrating to a newer stack. So another sample we took was in Latin America, and over there, QUIC, and this is from like last week, QUIC is now at 52% of volume for that specific carrier. Now, that's a big testimony to a mobile-first paradigm in our assessment, where essentially a lot of customers of this LATAM SP are effectively primarily using mobile phones and less of PCs, etc., which typically have a negotiation capability on the OS to choose between a TCP or a QUIC stack, or don't have it supported on the browser, etc. And you see a bit of a similar effect as I just discussed in terms of session density, where TCP still is the more chattier part, when content, large flows being delivered over QUIC. So QUIC has managed to break the barrier essentially in, let's say, a good 3 years to be the runner-up of dominant protocol, starting to push TCP more and more into a minority shareholder of the overall volume of traffic, which is incredibly phenomenal. And we'll talk a little bit about how the full stack looks. Now, I showed you quite a few slides around mobile traffic measurements. We did also some sampling on fixed broadband networks. Essentially, it's more of the same, with a different mix of origin where the actual content gets delivered from, because there's a lot of CDN, content caching, gaming. More things are happening on a wider spectrum of end devices in a fixed network than on a mobile network, as you obviously can imagine. But more of the same. So this is something that is not going away, that is for sure. And we kind of think about it as a sort of inversion of the equation, where you move from the fully distributed internet with connection first paradigms, with a very diverse set of important sites and destinations with some encryption, to what is becoming to be a very high UDP-centric environment with hundreds of important sites, not thousands or millions of destinations, all encrypted and mobile and cloud first. And we're really thinking in this way to ensure that whatever we build moving forward is actually going to fit this setup. And maybe as a small introduction to the broader full stack discussion, One of the main things that was built into QUIC is that it is super application-centric, right? The whole goal of a QUIC stack and why it was developed was essentially to keep the app at its highest performance capability given a set of constraints that you find in the network. Whilst in the past, TCP was essentially goal to create network fairness. So we could take certain assumptions around when you design networks that if you start dropping packets or doing something to the packets, TCP would exhibit a certain behavior, start backing off, the window would reduce, the amount of bandwidth consumed on the TCP sessions would go down and create like this equal playing field amongst the various apps running on the network, while QUIC actually just doesn't care, right? If you start, if you change the capabilities of the network, reduction of bandwidth, congestion, whatever, QUIC is essentially not going to back off. The TCP sessions will start doing their fairness thing, and essentially QUIC will start taking whatever highway it can get its hands on. And you see some of these measurements, right? One QUIC session, one TCP session, you double the TCP sessions, QUIC's throughput actually remains relatively constant as you're building up more TCP sessions. It just doesn't give anything away to others. By the way, the reason YouTube works this great is essentially because of this phenomenon. So, Andreas.
Thank you.
Walk us through the stack.
And by the way, these measurements, which we're going to go back into a bit later, have been done by the AP-NIC team, by Jeff Houston and his organization. They've been doing brilliant work in characterizing the behavior of multiple protocols. They've got some really cool slides on SlideShare that you can actually go and look up. I mean, that's where we learn from a lot of that stuff as well. And just coming back to the disclosure, because you're going to need to remember, QUIC actually doesn't do anything, unlike TCP, which has a behavior that's built into the protocol that because it's running system level. QUIC has pretty much the same algorithms, but it's the application that determines what's going to happen during congestion. And the application is not necessarily a friendly application. All they care about is their user experience. That's the fundamental thing that we need to be keeping in our minds. So we say QUIC, and we talk about QUIC, but actually we're talking about a complete protocol stack, okay? Because we had a stack that was HTTP 1.1, 2, even 3, over using some form of SSL, TLS, TLS 1.2, over TCP, and the standard TCP IP stack. And we're evolving to essentially what is looking like an HTTP 3 session stack with QUIC as its underlying transport protocol encrypted fully using TLS 1.3. And that's a very, very important piece of the element. Running over UDP, UDP, as we all know, being a fire and forget type of protocol as far as the networking is concerned. So what we were saying earlier, the application controls what happens when the normal packet flow is somehow disrupted. Congestion, drops, errors, whatever. But it's not just that, because we all know DNS, right? By the way, there's a session running which is exclusively dedicated on DNS, right in parallel with us. Unfortunately, we're only going to do a very small part of it. But DNS is transitioning from a classic 53 UDP hierarchical system to DNS over HTTP 3, which means that the DNS is now in an encrypted HTTP 3 pipe, and all DNS interceptions, redirects, and whatever, as we're going to see, are being very, very disrupted. And on top of that, the final piece in the protocol stack of the tooling that we'll look at in detail that we used to have to figure out where the hell the packet's going and where it's coming from, apart from the IP address, which is server name indicator and client hello, they're all getting encrypted as well. So we're starting to have a very, very big change. And the big change starts with TLS 1.3. I mean, I'm no security or encryption expert, but TLS 1.3 was a major change in the encryption world for the very simple reason that it's now completely uninterceptable. Man in the middle because there's no pre-shared keys, because there's no key exchange unless the application gives you the key. There is no way you can actually sit in the middle and actually decrypt the traffic. So the ability to peer inside what the classic DPI systems were doing 10, 15 years ago, and peering inside the packet and figuring it out is completely gone with TLS 1.3 because you can't decrypt even if you're sitting in the middle of the path in any way, shape, or form. And all of the encryptions that are being used by the extended QUIC stack DOH, ECH, et cetera, are all using TLS 1.3. Then you've got QUIC, which is being essentially touted as the new TCP by virtue of two things. First of all, its adoption, which, as we saw, is very, very rapid, but also because it's much more optimized, going back in history, as I was saying earlier, for RPC type work, because it's a one transaction on session initiation, and once the session is initiated, it's zero RTT. Everything is kept in place, which means that the user experience, and that's ultimately what the application provider cares about, right? It's the user experience. We all know if it doesn't respond in the first 3 seconds and you don't see something coming, click, go away. That's what everybody cares about. QUIC optimizes exactly for that. It also optimizes the ability of the application to do whatever it wants. And if the application, like YouTube, wants to deliver at all costs, you know what's going to happen. When they see congestion, instead of backing off and say, I'm going to be a nice netizen, all I'm going to do is, QUIC supports multi-session, doesn't it? 5 parallel sessions, shoot the same traffic over 5 sessions. The packets, some of the packets are going to arrive at the end. They're going to get reassembled by the application. Oh, but I pushed everybody else out of the way. Why do I care? It's my application. And that's the way it works. And this is a total change in the way that we actually deal with networks and we design networks, because we've got some implicit assumption. I mean, I've been in this business about 30 years, okay? It's TCP/IP. You drop a packet, it backs off. The world is a cooperative world, not anymore. Because the application now is in charge of what happens. And if the application is friendly, by the way, we're seeing, just to be fair to the application vendors, we're now seeing application vendors making noise about, we will manage our behavior if you do not throttle us. So it's becoming a little bit of a give and take between the application and the connectivity providers. But the thing is that right now, most of the QUIC systems are flood everybody so that I can get my user experience. And the cool thing is that it works. Uber did a really, if you look at the graph at the bottom there, did a really interesting test in India, I believe it was, where they tested their application on a QUIC stack and on a TCP stack on different kinds of networks, from GPRS all the way to Wi-Fi high performance. What they found is the worse the network, the bigger the user experience improvement, which meant that the QUIC stack and the aggressive policy that they were using in order to deliver the QUIC traffic was actually working the more congested and problematic the network was, which was total validation of, okay, if I've got problems, I care about my application, everybody get out of the way. And everybody does get out of the way with very, very unpredictable results. So QUIC, I'm being unfair to QUIC here. QUIC is not unfair, but it has the capability from the application perspective to become unfair in its usage of the network. And this has a lot of interesting impact on different service provider networks. I mean, for example, think about, because we started at this from a mobile perspective. Why? The reason we started is because if you look at a mobile network, the bottom band, the coverage band, 10 megahertz, 5 megahertz worth of bandwidth, that's the one that has most of the users on it. That's the one that, because it's got the widest range, and it keeps the connection in place. As a result, it's the one that gets congested most easily. what happens if you start overloading the scheduler on a radio network, when you've got 5 megahertz or 10 megahertz worth of bandwidth, it'll start dropping PDUs. The assumption, because that's a layer 1 device, the assumption in that system is, I drop the PDUs, that's essentially dropping down a whole packet because the CRC doesn't work anymore. A drop packet means TCP is going to get the signal, it's going to back off, the world will become nice and friendly again. Not anymore. So that is a very major impact in a network, and it's true of any access network, but it's also true in interconnects. You've got an interconnect with a specific, big, fat pipe with a specific bandwidth, and if you start dropping, you would have assumed that things would try and revert to normality. However, they don't. They just get flooded, and we'll see some use cases around these things. Now, traditionally, and even today to a certain extent, we've been using techniques that said, okay, let me do a little bit of recognizing of the flow, and I can start doing some policy on that flow, and maybe I can actually do something about it. But to recognize, you used to be able to actually delve into it, DPI, that went on away with TLS 1.3 over UDP on QUIC. Then I say, okay, I'll intercept the DNS query, that's no problem. I know where it's going. Nope, not anymore, because nearly 50% of the global DNS traffic has moved to DOH, which is essentially an application to server DNS query executed over HTTP. Cloudflare and Google serve 50% of the global DNS requests, most of them over DOH. Firefox in the US actually defaults to Cloudflare DOH. It doesn't go to your operating system anymore. It doesn't ask Windows or Mac OS or whatever to run through the recursive DNS stack, go through, get the result, and then open the connection. Opens the connection directly to a fixed Cloudflare setup, gets the address, and goes. So we're starting to lose that interception capability, and it's happening fairly fast. There's even DNS over TLS, but that wasn't quite as successful because it requires the complete DNS hierarchy to be encrypted, and that takes too much cooperation. We know that cooperation doesn't work very well these days. It's all about competition, right? And then we said, okay, but we used to have SNI, server name indicator, the fact that when you're going after a virtual server, which is hiding behind a CDN, I've got multiple virtual servers, there's something called SNI, and I can intercept SNI because it's in the clear, and I know where it's going, so I can understand what kind of application is going, I can start doing policy. RFC 8744 comes in and says, no more SNI, TLS 1.3 encrypted SNI. Well, that's okay, because the original DNS query is still in the clear with APPN. Oops. Nope, encrypted client hello comes along, brand new application. The only thing that remains visible is the content delivery network. And there's like, what, 12 content delivery networks, we said, that deliver 80% of the global traffic, and you have no clue, none of us has any clue, potentially, of what's going on behind them. So if you try to put all this together, what we end up with something that we really understood very well, which had been built over years to be robust, cooperative, and whatever, that we could actually have full visibility inside every level of the stack. You could look at addresses, you could look at content, you could look at transactions, you could look at flows, everything, and then one by one they go away. First we do encryption at the session layer, HTTPS, HTTP3, and whatever. Oops, one gone. Then we start doing it at the session setup layer. Gone is the DNS, gone is the SNI, gone is the client hello. Oh dear me, what's going to go on? Oh, now it's gone down inside of the transport layer as well. There's only one thing visible left, and that is source IP address, destination IP address, the classic 3-tuple, 5-tuple that we all know from our routing days. And that has a lot of impacts because there's no visibility. Therefore, all our classical techniques for actually figuring out what the hell's going on to do things to it are being impaired on a continuous basis. And that drives a global transition in the way applications are written. And remember, we saw the number of flows, right? There's a huge number of flows, but the ones that matter are the big guys that are carrying a lot of video, and they're the ones that are causing all the havoc around the network. You want to take this one, Bert?
But there's more. Yeah, sure. Essentially, this was the way things were happening. Aggregate fairness across TCP sessions, flow control that was well understood and behaved. And the IP network was doing a hop by hop, packet by packet processing and figuring out where to send the traffic. So with QUIC now inside the app being the flow control mechanism, the session mechanism, essentially things got much more difficult because flow scheduling, pacing, bandwidth sensing is all within the application space, user space, controlled by whoever is developing the application. So dropping, and this is kind of a repeat from what we said, but it's really important. Dropping it means back off is a very large assumption in networks, and effectively that is not anymore the case for roughly 40%, 50% of the traffic, right? Drop on TCP, reduce the flow. Drop on QUIC, just keep going if that's the behavior you're trying to achieve. So that is really, one of the big elements we want to point out. Now, in case you had any doubts still about whether this is a bit of a theoretical thing, we did some crappy measurements and it's all wrong. All these logos are fully on this in their respective, application spaces and application developments, right? So, and it's a very large set of players. And actually, there's zero proprietary capabilities here, other than how you want to drive the protocols. Everything is standardized, right? It's all in IETF. It can be implemented as we speak. So, the conclusion of looking at this stack is essentially there is a set of data that you can still glean from the network. First of all, you have to start including the user endpoint as well if you have control over it to glean information. There's CDN information, and then there is the temporal behavior of the IP network, IP packets as they go across the network that you can also ingest as a set of information to start looking at doing something to the traffic should you wish to do something, right? So it's essentially IP header inspection and logging, and then essentially looking at how the spacing and temporal behavior in time is for specific flows, right? Anything else you fish out of network observation is a bonus, but you have to assume it is going away, right? Especially, the CDN and the big cloud infrastructure providers are putting a lot of effort in moving forward and plugging any remaining holes of visibility or gleaning of SNI, etc., in their stack development. By the way, Google load balancing today is defaulted on H3 and QUIC, right? Just to give you an idea, a lot of developers who don't even care about the actual network protocol stack that they consume, they will just when they push out their apps, they're gonna consume that infrastructure automatically. So that's, we think, is going to accelerate also non-consumer application development towards the stack we just talked about, and we can see that already. So this is not a pure consumer environment, even though the data we showed is consumer level networks. We also see this happening in enterprise networks, right? So we got two pieces of the session left. One is a bit of discussion around relevance to service providers, some of the things we were thinking about, and then Andreas is going to talk about toolbox and use cases of what we could do with hardly observable traffic, at least in the traditional sense. I can't stress it enough, the consumer will see benefits, right? So this has always been the thing that drove adoption of new, nitty-gritty technology stuff that we just talked about. They are seeing benefits. The Facebook and Uber, to me, are one of the biggest in-your-face examples of, they looked at it and they said, they weren't like ahead of everybody developing these capabilities, but actually started experimenting and said, look, it's just going to be easier and better for us to deliver all this stuff to the end users in our application. Let's just go with it, right? For Uber, it's essentially a fight of getting that taxi reaction, the connection as fast as possible, so you don't switch to some other brand to get your taxi. No need for playing doomsday and saying everything is now FUBAR. But we do want to stress that to some extent this will pose challenges for some of the services that service providers are relying on, right? Differentiating billing capabilities, differentiating in terms of who gets to go first, traffic management, SLAs, optimization of traffic through packet inspection. How do you actually direct traffic to go on certain links versus others? And one of the very, I think, overlooked elements is that the content delivery and caching capabilities of service providers, in our view, just rose to a higher level of priority. For a long time, CDNs were considered like, a lot of operators stepped out of it because it was cumbersome, and you started putting the siloed caches of the Googles, etc., into networks. If you actually want to be part of the food chain of user to application, you have to be. The only way to do it is if you are actually delivering. If you're part of the delivery chain for the content, which equates in this case to a CDN, right? Because you have to have, the keys and credentials for the applications. Otherwise, this is it's invisible. And the impairment of Node B performance, Andreas alluded to it just a few minutes ago, is actually very, very important, right? So over here, the fact that you have implied assumptions in base stations about dropping packets and then creating a set of fairness is something that we expect to have to be revisited significantly, either through direct interaction on those node Bs, or through indirect interaction further up in the network by understanding what's going on, detecting congestion, and then taking measures to actually facilitate a level of congestion management that will help you to monetize your spectrum, right? So that's a very important piece. Now, obviously, you can imagine that if you have to start upgrading, all the way to the radio, your network, that's a pretty expensive game. So we'll talk a little bit about how we think we can do that in a more IP level capability further up in the network.
But make no mistake, this is not a mobile-only thing. This is true of any access network, any Wi-Fi network, anything that will, at some point in time, experience congestion because somebody's running a YouTube video, or somebody's running a meta video, or somebody's running any kind of big traffic flow. And it makes no difference, because the problem is, is layer 4 and up. It's not a physical layer problem. It's just that the physical layers, any physical layer, makes an assumption about what traffic is running and how traffic will behave above it. And that assumption needs to be rethought by what we're seeing.
Yeah.
Sorry, we tend to be repeating ourselves a little bit, but half of it is that it's really, really important to challenge our core assumptions on how we build and design networks. Yeah. The other half is we're also known as brothers from a different mother, and we suspect from a different father as well, but we're not entirely sure.
So, I thought this was a great visual to actually illustrate in another way the parallel internets that we have here. Right? There is no single internet anymore. If you look at the Google caching footprint, it is phenomenal, right? Over 10,000 edge pops across the globe. You know, some of the CDN players, Akamai, Cloudflare, Fastly, are built on a massive build out and have an existing footprint which is, you know, in the thousands of edge nodes. Microsoft is, you know, and AWS following, you know, quickly suit, right? So we think this is, you know, the peering of the future in terms of you have to figure out as an operator how you're going to get connected to these networks in an efficient way, and you know, actually deliver a differentiated experience to your end customers. So one thing we just wanted to click on, because I think it's an interesting setup. Who's heard about Apple Private Relay? Okay, we're all networking guys. It's the VPN of the future. I'll throw it out there. Apple is a pretty smart company in most people's books, and they actually took the stack that we just discussed and are using it today to tunnel Safari traffic all the way to their environment in a full, you know, obfuscated way on any underlying transport. And the reason they do this is because they seem to have decided that privacy is something you can monetize, right? Because they market it as a capability on the phones. It's an iCloud Plus subscription feature, where essentially they say, look, if you do this, then you're going to get less cookies, less, you know, advertisements, and you're going to get hassled a lot. We'll just hassle you. I guess that's between brackets what they put in. But they've built out this infrastructure where essentially you take the traffic, you put it on H3 and QUIC, dump it onto an Apple ingress proxy. They then, you know, onion route it anonymously out of an egress proxy and dump it onto the destination internet, essentially obfuscating which, you know, source is requesting, you know, whatever, making it hard for the people that sit on that green, you know, internet logo to figure out who's who and what to sell to the end user, right? So they've built out an ingress proxy. They have DOH included. They essentially run this on a private backbone and peering infrastructure. It also is a very good indicator around control of the endpoint. So it's essentially a mobile device management system without being called like that. A mobile device management system, which essentially is today only used in enterprise environments, right? You guys are all probably have company-controlled phones to a large extent. They've now essentially lifted that up to consumer scale, if you wish.
So, by the way,
yeah,
Apple didn't invent this. We dug into Google Chrome And we found that Google has actually been supporting this kind of functionality on Chrome for about 4 years already. They've just done a piss poor job of marketing it. But in reality, they're not the only ones. And the parallel internets are moving from a CDN to a complete source obfuscation, destination obfuscation.
Yes.
Apple, Google, I was 2 out of the 4.
Yes. So the whole, service provider domain, essentially, in this way, is bypassed in an enveloped tunneling mechanism over H3 and QUIC. And the way we think about it is that the ingress proxy has now become the new services and identity anchor point, right? Because exactly there, only Apple knows who you are, what you're doing, what they should do with your traffic, whether there's SLAs or not. Today, a consumer application, who knows what is going to be, in 12 or 24 months. It is sort of a VPN without being a VPN because it's just IP routing, right? But it has, quite some potential, we think. Now, some SPs already come to us and said, look, all of this stuff is getting us in trouble with regulatory, mandates where, for instance, illegal gambling, the way a lot of countries are trying to deal with it is that, they do DNS management and they start blocking sites. It's a cat and mouse game. It's not, 100% good and always bulletproof, but it is being done. Now, with this kind of setup, what are you going to block? You're going to block Apple? Well, I guess you're going to get a lot of customer calls then, right? So those are things that are, pretty complicated now. We've also had, discussions around, zero rating of apps, volume. Now, there's another side of regulation that kind of kicked into that, and everybody has to have a fair playing field. So some of that was less of an issue moving forward, but still, there's no way to figure out where this traffic is going other than going to Apple. If you have an offering that says, my application is for free traffic-wise, if you do volume-based billing, etc. So. Another thing we wanted to discuss in this setup is that essentially in service provider land, there's a lot of discussion around edge services, pushing capabilities closer to the end user, reducing latency, getting a higher SLA or higher experience for customers. Now, if you have a setup, a normal setup, essentially, user pushes a request from Austin, the servers figure out that the cached version or the edge service that you can invoke is sitting in Austin because of the geolocation, and essentially the customer is served from a closer point his content. Now, in a Apple Private Relay thing setup, sorry, it's a thing, it's a setup. The request will potentially be routed out of another geo area than you would normally expect it to be, because you have no control of it as a SP domain side of the equation here. And the application on the internet is going to say, oh, this guy is from Denver, let's send him to the edge content caching, whatever, in Denver, essentially starting to loop that traffic all the way back into into the backbone of Apple, all the way to the user. So what have you just achieved with your massive investment in edge services if this becomes the de facto situation? Now, honesty, forces me to also say that the intent or the incentive for Apple to make us here in Holland look like we're from Mexico or from San Francisco is very low, but more fine-grained geolocation-based figuring out where to redirect traffic to will essentially remain an issue, right? So we think this is something that if you're designing some of these capabilities, low latency, whatever the case might be, this is something that you cannot ignore. Again, that means you have to be part of the application space. That's what this implies. So, speculative view, big disclaimer, what this might lead to is essentially, a bunch of parallel H3 QUIC big tunnels coming out of phones, computers, etc., all racing towards their, big cloud destination where, full control sits with the application, and your phone looks like, essentially a massive, tunneling system of traffic to a very discrete set of destinations. Very different from what most people envisage, a distributed IP network to look like. And so, yeah, we think, and we are seeing, quite a bit of operators already looking at, various elements of their portfolio to do an assessment to what stays relevant, what needs to be adjusted to actually remain accurate, what can still be done, what needs to be dropped from their portfolio, and so on and so forth. And we are very, very adamant about this because there's no point in having our customers invest in networking technology unless it actually contributes significantly to what you are trying to achieve, right? So we think that whilst you think about network infrastructure, you actually have to think first and foremost about the client-server architecture that you are dealing with. If it's an enterprise environment or a consumer play, that might lead to different conclusions, IoT, etc. Secondly, really think about parallel internet and what it does to your demand matrix and network planning and these elements, because I think there's a lot of kind of hidden assumptions that were made, long time ago that now essentially need, thorough investigation. Undeniable, make sure, teams are aware of this protocol stack. I think, in our experience, there's quite a number of folks who are looking at an IP network, kind of abstracting the rest of the stack away and not taking into account what we just discussed. And for us, it really leads to a conclusion that there's going to be significant simplification of some of the interactions that happen with networks, and they're also going to change in terms of how they're being done, right? So a lot of inference of conclusions rather than seeing direct conclusions right in front of you because you've observed a set of flows in the network themselves. So let's talk about that a little bit in terms of toolboxing.
And a glass of water, if I may.
Yes, you may.
I owe you eternal gratitude. So, let's be clear. I wish I could say that, we sat in a room, a bunch of really smart people, and came up with all this. The reality is, there was trouble. There was trouble in the tavern, as they used to say in my country, and it came in the form of questions from service providers. I'm going to tell you a couple of true stories that kind of sparked this operation. Certain major carrier gets a phone call from Snapchat saying, excuse my language, and I know this is being recorded, your network is horrible. Okay, I'm not going to say the bad word. It doesn't work. My customers are complaining. If you don't fix it, I will actually redirect all my Snapchat users to use other networks. Oops. That's not something you want to hear from a major app like Snapchat coming to the CTO of a major network. Same network, by the way, and that's only because they talk to us. I'm pretty sure pretty much everybody else has been getting similar calls. Got another call from their internal marketing people saying, we're seeing a lot of noise in the chat rooms about the fact that our new 5G network is junk. And what they're actually saying is that, but I measure the performance, the throughput, by downloading a video from YouTube Premium, I'm sorry, and it's like 4 megabits. Where the hell, or 4 gig, whatever. It's a joke. What the hell's going on? And they looked at it and said, oh dear me, we actually have a policy which says that we're actually assuming that Snapchat traffic, because we were doing DPI and we could actually understand what it was, is video, and was rate limiting video to 1K, so that it actually downshifts to 1080p. Or we're doing the same thing with YouTube, except Snapchat doesn't work this way. Snapchat has a video stream. I learned this from my son. I had no clue what the hell Snapchat was, filters and all that. So they've got one stream that's video that they're transmitting, and there's another stream which is those moustaches and glasses and strange things that they go and snap on top, and they make those mixed reality setups. Well, if you treat both as video, the moustaches and stuff was not downloading fast enough, and it wasn't going on the right place on the video, and the Snapchat user were getting horribly pissed off. Same thing with the YouTube thing. YouTube Premium, unlike YouTube, is not just streaming, you can also download. So they were going downloading, but they were thinking it was streaming, and they were actually rate limiting as if it was streaming, and then they were seeing a much, much lower performance. This is because of the obfuscation of the traffic that has been happening, and because their DPI systems were not capable of distinguishing between those environments. So they came to us and said, we've got these problems, guys. By the way, you should know about these things. We don't know how to differentiate from a download versus a streaming video from the same source. Oops. That's a major problem, because we're supposed to treat them differently. In their minds, it was their policy, not ours. I'm not saying that I advocate their policy or not, but it was their policy, but they didn't know how to apply it properly. That was a big, big, big issue. So we kind of went back, we did the measurements, we did the understanding and everything, and we saw, okay, it's obfuscation, it's QUIC, it's TOH, it's all of these bits and pieces that are buggering up completely our capability of being able to understand what the hell is being traveling on our network. And it also buggers up accounting, by the way, because if you can't see the actual server, how can you do application-based level accounting? Blah, 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 blah. Zero rating, all the stuff that Bart was saying. What do you do in these cases? Well, it turns out that there is information that we've never bothered looking into. And that information is the temporal behavior of a piece of traffic. Different kinds of traffic actually behave differently in the time domain. Even the same kind of traffic between protocols, because of the protocol interaction mechanism, actually behaves differently in the time domain, which means that I can actually tell, even if it's totally encrypted, that a flow is a TCP video stream, because an ABR video player is an ABR video player is an ABR video player. It'll do get the first chunk, buffer, and then keep buffering to make sure that I've got enough stuff to play back, irrespective of how bad the network is and my user is not impacted. So I'm going to do that differently on TCP and QUIC, only because QUIC is a much faster interaction, so I get a lot more traffic in the first burst. It's really, really good at that. But for example, a live stream, a WebEx video conference, a voice call or whatever, has a complete, even though it's UDP again, at the underlying layer, it's got completely different temporal behavior. And a download has absolutely no regularity. It's yet another different thing. That means that we can't anymore have the amazing wealth of information of a clear text protocol stack, but we've got cool information which actually addresses the problem statements that certain carriers were actually setting to us, and actually addresses it in a very large way, because if you remember, we saw the traffic statistics, right? QUIC is being used the obfuscated stack, shall we say, is being used primarily by large-scale video flows, which are the big bulk, well-known Pareto principle, 80% of the traffic is generated by 20% of the flows. Okay? So that led us to start thinking about doing traffic management in a flow environment rather than in a per packet environment. Because how do we build networks these days? We route IP packets. So we deal with everything on a per packet basis, and we don't manage traffic. We may cut traffic, with Hackle's example, on a per flow basis, but we don't manage traffic on a per flow basis. And we've been working with other friends in the industry to build a toolkit that we can use to assemble useful use cases that we can actually push in this direction. The first one is time domain flow recognition, because it's not good enough. Okay, they have a signature. We saw that. They have a very, very clear behavior. However, time domain flow recognition means I need to be able to understand this behavior very, very quickly so that I can actually respond within milliseconds. When we first talked with his boss, actually, who is a real old-timer in the networking world, and we call him the chief cynical officer sometimes because he will question everything. And when we talked with him, he said, hold on, how fast can you do it? Because if it takes you 3 seconds to do it, who cares? So we need time domain flow recognition tooling that can do it in a few milliseconds. 1, 2, 3 milliseconds to actually tell you, okay, this is a TCP or a QUIC video stream, regular downloads, or whatever. The second piece that we actually realized is that if you try to manage every flow that you have on your network, we saw the numbers earlier. The number of flows is huge. You get into, again, a scaling issue. But do you really need to? Does anybody care about the 3-packet transactions from DNS or the, ping, pong, ping, ping, sin, sin, ak, ak, send a packet, close? Nobody cares about those. They don't do anything to the network. So does anybody care to do anything if the network is running at below 100%? No. So the other thing that we need to know is when to start dealing with traffic. And that means being able to infer congestion in real time and understand where it is happening. And that is essentially a piece of tooling that uses some pretty cool machine learning. And in conjunction with the various congestion management protocols. By the way, QUIC uses exactly the same one. Reno, QUIC, BRR. They just use them in a different way. Okay? In conjunction with those protocols and a lot of application flows, we can actually learn in the models how protocols behave. If we know how protocols behave, we can actually do anomaly detection. If we can do anomaly detection, we can understand that there is congestion happening within that specific flow. The only piece that's missing, which is fairly easy to get from signaling in various, or addressing in various forms and cases, is, okay, which link does this flow belong to, so that I can understand which other flows are affected because they're sitting in the same link, or can potentially be affected. So these are pieces of tooling that we kind of been working on and putting together. And then the third piece is, okay, if I can figure all these things out, then I need a mechanism to do programmable traffic management, to be able to apply policy, which is nothing new, right? But you need to bring that into the package to do programmable policy management on that particular traffic that I've been able to identify, find the right time to do it because it's happening in a congested area, and then I'm going to do things. And essentially that leads into a system logic, and we're not presenting a product to you here. Let's be very exact. We're presenting you a toolbox that we've put together over the years, and we've built some instantiations of in production, some others we haven't, but they are just different assemblages of the same tooling. So we said that what do we have in a network that we're never going to lose? We've got source destination tuples, because you got to root. You know, if we lose that, then we're not rooting. We don't do anything. We can go home. We're done. Okay. We also have packet interval and packet size. These things never go away. If we know that, we have what? We have source destination and temporal behavior. Once you've got those, you have the ability to recognize. If you can infer congestion by profiling applications, profiling flows, and whatever, then you can actually start saying, I'll start putting my policy engine to do control when required, to who it's required, or to whom is amenable to it. Remember we were talking about ABR flows. I'm going to go back into it, let me not repeat it. So the use cases, we started putting a lot of use cases around this. The first one, which we found, which kind of came for free, was, okay, if you're going to be doing this, you're going to be monitoring stuff, right? It turns out a lot of customers around the world, a lot of service providers, don't really monitor their network to do protocol analytics and flow analytics and whatever. That comes for free because in order to do all the recognition, we've got to have that stuff. It's in the LK stack, Kibana. On top of it, you can manipulate the data in any way, shape, or form you like, and you can get all those cool graphs that we were showing in the beginning in near real time. The snapshot from Latin America was literally done in near real time. Oh, we haven't looked at Latin America. Let's log on to a network. Boom, snapshot, take it, put it in place. If I break it, they're going to charge me for it, I'm sure. So, on top of that, we have already a product that takes all these pieces and puts them in a specific use case, which is video user experience optimization, primarily for mobile networks, called QUIC, stands for Cisco Ultra Traffic Optimizations. It comes from the mobile world, which is why we have a little bit of a mobility bend and approach. It's also where I work most of the time, as an example. And it uses this toolkit in the following way. Remember we were talking about ABR video players, right? ABR video players buffer as much as they can, which means that they've always got a couple of minutes worth of playing time sitting inside your phone while things happen. Now, if I can recognize that there is congestion, red area in the network, and I know that this is a video streaming flow because I've done temporal analysis on it, then I know that that video streaming flow typically has a buffer, so I can actually hold it back if I have enough memory in my forwarder for 3 milliseconds, 4 milliseconds, no more than that. That will release enough PDUs in the radio network, get the other traffic out, release it back in, and the user experience is not impaired, but the congestion model has actually been alleviated. This is really, really cool because it has zero protocol dependence. It can be encrypted up the wazoo, and nobody cares because we recognize the type of flow. All we need to know is what happens at the IP layer. And yet, we can actually impact application performance. It's really cool. I like it, in all honesty. And if you actually put it in production, this is a real test case from an operator. You're running Ookla in a congested environment. You turn this technology on, you turn it off, and you get enormous improvement in Ookla performance because I'm removing congestion from the cell temporarily by just buffering a little bit of flow, which is bufferable, and nobody knows about it. By the way, streaming video is like 70–80% of the internet. So 70–80% of the internet is actually bufferable, quite happily, for now anyway. We'll see what comes up later. Similar use case, we applied it in Australia this summer, and it was actually a pretty cool one. NBN in Australia is the major access provider, right? And NBN operates as a neutral access provider, and the ISPs go and connect with a pipe to NBN, and they get their users through it. Typically, the ISPs work with a committed information rate pipe, which has a burst capability. Say if you've got 80 gigs worth of committed information rate and 100 gig physical with a 20 gig burst capability. But that 20 gig burst costs. Every time you burst over your committed information rate, you get charged a pretty penny. So what do? They said, okay, what if I put Policer on my link at the output of my CIR link at 80 gigs? I don't want anything, but that's going to cause user experience problems, because once you burst over it, you're going to start dropping packets, and all hell's going to break loose. We don't like doing that. But what if I put essentially a Qt-type engine that does flow recognition and flow buffering behind it? The moment you start dropping, congestion appears. Congestion is inferred by the flow manager. The flows that are bufferable get buffered. I slow down, I get it, I smooth it out in the temporal domain, it goes out. It's not panacea, because if you got 100% 100 gigs trying to go through there, eventually that's going to fail. But if you have any kind of burstiness in the traffic, which is the usual thing, it's actually going to save you, it's saving these guys a lot of money. These are two use cases of a larger use case, which is essentially the original question that was posed to us. How do you do custom policy based on flow type and whatever? What we were saying earlier. Detect the stream, figure out what kind of stream is, figure out what your policy is for that stream. Is it buffering? Is it policing? Is it whatever you want to do? Is it shaping? It doesn't matter. You can actually now apply it. But it gets better, because you can assemble it. TCP optimization is a really well established technique in especially the mobile world, right? And you know what TCP optimization does essentially, right? It essentially emulates fast start, so you can get the first megabyte really, really quickly out. Because remember what we were saying earlier, if I click and I don't get a response in a second, next. So TCPO is designed to counter that. The problem is that, and we ran a measurement, we're all about measurements here. We ran a measurement which said that during the course of a day in a telco network, there were 26,516, if I remember rightly, different optimal TCP windows during the day. TCP optimization is typically done with one optimal window, which means that there were 26,515 wrong TCP optimization windows during that day. What we've done is we've actually added an extra piece in the toolkit, which is crowdsourcing TCP windows and then allocating those TCP windows according to traffic conditions, congestion conditions, traffic conditions, and changing the TCPO window dynamically depending on link and traffic. That gives you a much more optimal little TCP optimization tooling, which, by the way, is really performant. We're talking about gigs per server, hundreds of gigs per server, that will actually do this kind of thing. Another one which we haven't implemented, but it's fairly easy, so I wanted to throw it, and the reason we haven't implemented it is because we've never had an actual customer request for it. It's fairly easy to build, is protecting real-time traffic. Remember, we showed that a WebEx, a phone call, or whatever, has a very, very specific and very clean temporal behavior. You can actually measure the bandwidth requirements of that very, very easily. And then you say, okay, here's the bandwidth requirements, that's going through that link. So instead of doing policy on the whole link, I'm going to do policy, optimization, video, whatever, on the link minus that particular flow, which means I've now protected the real-time flow, and I can actually use that as a feature. I haven't seen anybody asking for it, but we thought it was cool, so we put it up here for fun. The interesting piece is, why does this technology and these things scale really, really well? Because we don't do it all the time, and we don't do it to everybody. We only do it when required, when there is some kind of congestion event, which means you need to do it, because if there isn't a congestion event, who cares? let the traffic flow, let the good times roll, okay? And only on traffic that is amenable to treatment and big with a capital B, so that any impact you have is major, which means I'm only doing it 20% of the time on 20% of the flows, which means that I'm using state, the dreaded state machine, on a much smaller scale, and therefore it can scale to a much, much, much larger network deployment like the internet. That's why we really like this kind of tooling and the games that we're playing with it.
So that concludes our session a little bit earlier than the time allotted, but I'm sure this is the graveyard shift of after lunch and what have you. You won't mind. But seriously, I hope this session gave you a bit of a view of our current thinking and activities around encrypted traffic, controlling it, recognizing also how application stacks are evolving and fitting that into the networking space. DPI, just be aware, you're not going to catch everything. You can figure out yourself how much of your traffic is unobservable, but those DPI engines will probably miss them. If you're a service provider, maybe some food for thought as to how this affects some of your capabilities, what are cost implications. We didn't stress too much the CDN piece, but I think that's a big kind of entry point on the agenda to look at it and understand what you can do there to be part of the end-to-end chain. And also give you a glimpse on some of the pure IP techniques that we're using to actually affect some of the traffic behavior in a non-disruptive way for the end users, right? Because that's the eyeballs rule. We need to respect that.
If there's two things we really want you to go away with out of this, is A, challenge your assumptions on network design. We have been in a specific network design mode for the last 25, 30 years, which is becoming less and less real. What we assume, and I'm talking about network design, and even talking about system design, everything that we have been thinking about is being seriously challenged, and we need to think about it. And as a result, start thinking about how you manage flows rather than how you manage just packets. Packet management is superbly important still, it'll never go away, but now we're going to have to make sure that implicit flow management ain't going to cut it anymore. It's going to have to start becoming more explicit. With that,
we'll leave you with the mandatory slides about using the app and giving us hopefully a good session survey.
We need to be invited back next year, so.
Thank you very much.
Thank you very, very much.